Good morning, everybody. I'm Dr. Joanna Albawa. I'm the Science Education Program Manager at Lawrence Livermore National Laboratory, and I'd like to welcome you to this year's Science on Saturday series. And the series this year is all about space, and it is truly out of this world. So I'd like to introduce our presenters today. Dr. Megan Brooks-Sayal is a leader in the Planetary Defense Group, and she got her PhD in planetary geosciences from Brown University. Joining her today is Mary Berkey, who's a postdoctoral fellow at Lawrence Livermore Lab, and she got her PhD at the University of Chicago in nuclear physics. And Dan Burns is a retired teacher from Los Gatos High School, and he got his Bachelor of Science in Aerospace Engineering. So welcome, team. Let's get started.
All right. Planetary defense is a relatively new field of study focused on an important question. If an asteroid or comet were going to impact the Earth, what could we do to protect our planet? And it turns out at Lawrence Livermore, we've been thinking a lot about this problem. You may be familiar with this scenario. It's probably the most infamous asteroid impact of all time, at least here on Earth, and it's the one that took out the dinosaurs 65 million years ago. That was a really bad day for not just the dinosaurs, but the other 3/4 of plant and animal species that were wiped off the Earth after that event. And that I need to emphasize this, because that was a really big impactor. That was a 10-kilometer size asteroid, which is like the size of San Francisco. And it obviously did a lot of damage, had global effects. And you may ask, okay, 65 million years ago is a long time ago. Do we still worry about impactors that big today? And it's true that over time, as the Earth has gotten older, the rate of impacts from these big things has gone down a lot. But if we go a little bit more in the more recent past to 50,000 years ago, we can see something created in northern Arizona called meteor crater. So 50,000 years is 1,000 times more recent than the dinosaur killer asteroid. And this was created by something much, much smaller. And you can see on the visitor center on the right-hand side gives a sense of scale. This asteroid impact crater is about over a kilometer in diameter. It was created by something that was only 50 meters across, so half a football field. It was an iron-nickel asteroid, so it's very high density, which is worse in terms of destruction. And it was, because it's so well preserved in northern Arizona, it was the first identified impact crater here on Earth, where scientists came to a consensus. This came from something that came from outer space and made this. If we go an even more recent history, just 7 years ago, 7 years and exactly 1 week ago, February 15, 2013, the Chelyabinsk impact event occurred. You may have heard of this. A lot of Russian dash cams caught it. Chelyabinsk is in Siberia, Russia. This was created by something not very big at all, 20-meter diameter rocky asteroid, and it brought in 500 kilotons of energy. So that's 500,000 TNT equivalent kilograms of energy. That's a lot. Thankfully, it didn't kill anybody. There was about 1,500 people injured. But we want to know about these before they're going to happen. So this was totally unexpected. It was a surprise meteor. And that's partly because it's so small. Things this small are very hard to see. Asteroids in general are dark and hard to see with telescopes, and especially the little ones are hard to find. And an air burst like this, where it's depositing most of its energy in the atmosphere, can still be very devastating. This mostly just blew out a lot of windows. But if you go back 100 years to the Tunguska impact event in 1908, that was also in Siberia, a very unpopulated region. It was bigger than this, and it brought in about 20 times more energy, so 10 megatons of TNT equivalent of energy, flattened 2,000 square kilometers of forest. And thankfully, there were not a lot of people around. But something like that over an urban area could be really, really devastating. Here we're looking at all the impact craters that have been identified on the Earth since 1959, when meteor crater was first identified as an impact crater. And it's really striking, I think, if you take a pair of binoculars and look up at the moon, that you can see so clearly preserved all of its impact craters, all of its bombardment history by asteroids and comets. And the moon, of course, has no atmosphere, no oceans, no vegetation, no tectonic plates to recycle the surface. But the Earth, on the other hand, does. And so it does not preserve this record very well. It hides the scars of the past very effectively. And so it's taken a lot of detailed analyses to find all of these craters, depending that scientists can look either at chemical analyses or look for certain phase changes from high pressure shocks, high temperatures, or they can look at geophysical data sometimes from space to find these craters. But the very first one found is right there, meteor crater. The scales are exaggerated a little bit, so the biggest things are a little bit bigger than they are in reality to allow you to get a sense of the relative scales between something like meteor crater and some of the bigger ones. A meteor crater in northern Arizona there. There's also a color scale. So meteor crater, because it's newer, is red. It's less than 1 million years old. The oldest ones on here are colored gray. So Bredefort in South Africa, Sudbury in Canada, those are ones that are more than 1 billion years old. And then Chicxulub is more commonly known as the dinosaur-killing asteroid. That impacted in Mexico near the Yucatan Peninsula. And that was conclusively identified, I think in the early 90s, so relatively recently as well. So our modern understanding of how often the Earth is being impacted by asteroids and comets has been rapidly evolving. It's also interesting to think about things that are smaller and how frequently those are coming in. Every day we're getting hit by small things, but we don't feel it here on Earth. Most of that material comes in the form of small dust particles and leftover remnants from comets and asteroids. And if we look up at the sky and see a meteor shower, that's little particles that they're burning up and radiating light. So this is a Perseid meteor shower example. And it's a lot of material if you add it all up. It's something like 50 million kilograms of material a year, which of an elephant is 5,000 kilograms. So that's about 30 elephants a day that's just kind of dumping dust onto the Earth constantly. But what we're really concerned about are bigger things that could make it through the atmosphere and do a lot of damage. And so we're going to take a little tour of this inner solar system. Jupiter's orbit is indicated by the yellow circle. And the Earth's orbit you can see as the gray circle, and the sun is at the center. And we're going to play a little movie where it'll show how the understanding of how many near-Earth asteroids are in our neighborhood has been changing over the last 20 years. So we start in 1999. All of those little blue dots are near-Earth asteroids. And then 2009, a lot more near-Earth asteroids. And 2018, a lot more near-Earth asteroids. So those asteroids have always been there. It's just we hadn't found them yet with telescopes. And now we're adding in all the brown asteroid belt asteroids that you can see in that brown loop there. Those are safely staying in the asteroid belt. They're not going to be a problem for the Earth. It's only when things are perturbed out of the asteroid belt and come into Earth-crossing orbits that they can be a danger to the Earth. And that happens through interactions with Jupiter or other dynamical processes. And so scientists are discovering near-Earth asteroids at a rate of about 2,000 new ones a year. But we're going to see that there's a lot more even beyond those discoveries. There's many that they're missing still. How do they look for these? Well, they use telescopes, and you probably are familiar with the electromagnetic spectrum and the idea that light comes in multiple wavelengths. Where we can see as humans with our own eyes is only a very small part of the spectrum, in the visible or optical part of the spectrum. And that's shown by the image on the far left, the Pan-STARRS telescope, where it's pointing to on the spectrum. That's a telescope that looks in the optical part of the spectrum. And that's one of the big heavy hitters for identifying new near-Earth asteroids. Also, Catalina Sky Survey in Arizona detects a lot of new near-Earth asteroids, and a handful of other telescopes as well. We can go to slightly longer wavelengths in the infrared. That's a really good place to look for asteroids. So a dedicated space-based observatory is what we're really hoping comes to fruition in the next few years, such as the NeoCam telescope proposed by NASA's Jet Propulsion Laboratory. That would be a really good asteroid hunter just to have in orbit around our Earth, looking all the time in the infrared. If you look in the infrared, you can find out more about the asteroid's composition typically. And you go to even larger wavelengths, out to radio waves, and use a facility like the Arecibo telescope in Puerto Rico, which if something comes really close to the Earth, and typically you would know from other prior observations, and then you could use the radar techniques to get really clear images of its shape. And that's shown as an example here. This asteroid ended up looking a little like a skull, and it was imaged right before Halloween, so it got the nickname Spooky, which I thought was really fun. What happens when we get to visit an asteroid up close? When a mission from NASA or JAXA in Japan or ESA in Europe sends a spacecraft and is able to take very detailed pictures, you get something like this. This is from NASA's OSIRIS-REx mission, which is in orbit around this asteroid Bennu right now. It's going to bring samples back to Earth for analysis, which is just so exciting. We'll learn so much more about asteroids that way. But you can see it's got this amazing varied texture. It's a rubble pile, and we often refer to asteroids as rubble piles because they tend to be very collisionally processed. They've undergone a lot of impacts in their histories, and so it's kind of a grab bag of boulders and rocks and smaller materials all mixed together. There's a lot of unanswered questions about what the internal structure might look like for some of these asteroids. Another way to think about asteroids is that they're the leftovers from planet formation. So when our solar system was still accreting into the planets in the inner solar system, like Mars, Earth, Mercury, and Venus, some of it got left over, and those became the asteroids. To give a sense of scale, Bennu is about 500 meters across. So that's about the size of a very tall skyscraper, like the Sears Tower in Chicago. And I should mention that it's not quite spherical. You can see it at the waist. It's a little elongated, kind of like a top shape. And there's a lot of variations in asteroid shapes out there. Some are bilobate. It's really interesting to see how exotic they can be. Another exotic thing about asteroids are they have very low escape speed. So if you were an astronaut at one, the escape speed would be only a few centimeters per second. So you need a way to tether yourself. If you move even very gently off the asteroid, you would fly away and not necessarily have a way of getting back. So it's a very exotic, low gravity environment. Here we'll go over where a lot of the risk today is coming from different size ranges. So at the top, things that are 1,000 to 10,000 meters across, things like that. There's about 2,000 total of them out there in the near-Earth object population. We can look to Mount Whitney, the tallest mountain in California, as an example of something that big. Luckily, 94% of those are very well characterized. They're not going to be a threat to us anytime soon. So even though they'd be very devastating, we don't really worry so much about those. They're very well characterized because they're easy to see with the telescopes because they're so big. If you go down to the lowest size range here, less than 10 meters, there's 500 million of them out there, and we haven't seen very many of them because they're very hard to find. But those won't pose a risk to us here on Earth. Most of that energy will be deposited in the upper part of the atmosphere, and there will be no problem with those. So it's really the middle two categories here, the tens to hundreds of meter size range, that we focus a lot of our energy on right now. Things that are 100 to 1,000 meters in diameter, there's about 130,000 of them out there still. Only 18% of them have been observed. That means we don't know where most of them are. They could impact at any time potentially. So we want to find them before they find us. And things that are 10 to 100 meters in size, there's 10 million or so of those out there, and only 0.5% have been identified. So again, there's a lot of work to be done on this. And the US for a long time has had an interest in planetary defense. And just 2 years ago, the White House came out with the Near-Earth Object Strategy and Action Plan so we could be better prepared for what to do in a real emergency. And the first aspect of this has 5 components is pretty obvious. You want to find more asteroids. So spend more resources on telescopes that can find those asteroids. The second, which Mary will talk about in more detail a little bit later, are the computer simulations that we do a lot of at the lab. If you want to prevent an asteroid impact, you have to do something to it. You have to nudge it off course. We want to know how to respond, and that requires very detailed multi-physics, often 3D computer simulations. The third component is mission technology. You want to be able to field missions to these asteroids, to test our technologies, to understand more about asteroid characteristics, to know how they'll respond. Fourth is the cooperating internationally. This is a very global problem. It can affect any of the countries on our Earth, and there's a big impulse to get people working together and getting on the same page about these types of issues. Last, there's emergency procedures. So for something like Chelyabinsk, you probably wouldn't deflect it. It's that small, but you just want to evacuate the area or tell people to stay away from windows so they're not injured. But having a plan in place ahead is really key for reducing some of the injury rates that could be felt by these. And I'll hand over to Mary, who's going to talk through more of the details of our deflection calculations.
So, good morning, everyone. I think it's still morning. So Megan, as Megan said, we have people working on a plan. So we are working on this. But what would happen, say, if NASA was looking through one of their telescopes and they see something, and they go and they do their calculations, and they come back and they say, all right, we see an asteroid, and we've done the calculations, and here's the Earth's trajectory, here's the asteroid's trajectory in red, and it's heading right for us. There's going to be a collision. We've got maybe a few decades. What are we going to do? And so now I'm going to tell you what the plan is for now. There's a few different things that we could do if this were to happen. I'm going to show you 3 different options. The first is called a Kinetic Impactor. This is a pretty straightforward plan. So the idea is, we're like, okay, NASA, you said an asteroid's coming. We're going to see where it is. Then we're going to run over to NASA and say, please let us borrow one of your rockets. And hopefully they'll say, okay. And then once we have the rocket, we'll stick a spacecraft on there, a very heavy one, filled with rocket fuel. And we'll launch it into space. And then we'll give NASA back their rocket and say, hopefully we don't need this later. Once our spacecraft is in space, we'll send it on its merry way to the asteroid. And it'll get there. And the idea is, with enough speed, you will ram it into the asteroid, and you will destroy your spacecraft. But all of the momentum that your spacecraft has built up will be transferred to the asteroid, and it will give it a boost of velocity. In addition, if you've made a big enough impact on the asteroid, there'll be some ejecta that'll come from the crater that you made, and that will be ejected in the opposite direction that the asteroid is moving, and will in turn give it an extra boost of momentum. So all of that's great, and the idea is, even though your spacecraft might be quite small compared to your asteroid, if you've only given it enough change in velocity, say like a centimeter per second, which is roughly like if a spider's under your seat right now, and it's probably walking at roughly a centimeter a second. But with a few decades, that small change in velocity is enough that we can cause the asteroid to have enough change in trajectory so that it'll sail past the Earth, and it'll still be intact and no longer a threat. And all will be well. The day is saved. So, and now Dan is going to demonstrate how to do that with a skateboard and a helmet.
Always a helmet, right? So Megan and Mary are looking at using collisions to deflect an asteroid to keep it from hitting Earth, and so we're going to learn a little bit about the physics of collisions. And so I have here a medicine ball, and I want to deflect myself this way. What could I do with the medicine ball? Throw it, right? Which way, though? The other way, right? Everybody knows that. Hey, it worked. A little bit anyway. And so what we just saw is a demonstration of momentum. If I wanted to move further, I could get a heavier ball. That'd be a bad idea, but I could. Or I could throw it faster, right? So both things are involved, the mass and the velocity. So that's what momentum is the product of the two. The more momentum I give the ball, the more I get by throwing it. Well, now I want to move that way, but I don't even have the medicine ball. Mary's got it. What could she do to get me to move? She could throw it to me, right? And that worked too well. But I moved about the same distance. And so this is a lot like the Kinetic Impactor. Kinetic Impactor hits the asteroid, sticks to it, and then they move away. And that hopefully is effective enough. But still not a really big deflection. I want to move more than I did in either case. Mary has the ball. So she could throw it to me, and then what would I do after that to even go further? Throw it back. But I'll miss her, hopefully. And so I did go further. And so some people think, no, if you hold on to it, that's going to work better. But in this case, if you think of it instead of just a catch or a throw, it's combining the two. If I catch it and throw it, it's more effective at changing my momentum because the change in momentum of the ball is even larger than that. So let's see if we can use that idea to maybe explain something that might be a little puzzling here. So I have this little battering ram with a rubber ball on each end, and I want to change the momentum of this board. In other words, knock it over. And so I pull it back. Oh, almost, but not quite. But if I put it on the other side and try and do it the same, hey, it knocked it over. And so did anybody notice why it fell over on this side? Well, it was different. Usually people are watching the board. This time I'll hold it and see what happens. And so on this side, it's hits, so that's like a catch, right? And then it throws it back. So that's a catch and a throw. That's called an elastic collision. On this side, not so much. It just kind of comes in and hits, it bounces a little bit. And so the materials matter as well. This is more like something called an inelastic collision if it hit and stuck. And so even though it's a rubber ball on each end, the materials behave differently, and so that would be important for an asteroid deflection, is understanding what it's made out of, its composition. Now, why does one side bounce and not the other? You can get these really cheap bouncy balls that only bounce 100 times. And so this one I bounced 98 times before the show today, 99, 100, then it's out of bounces. To get another, no, I have two. And so even though they look the same, this one, when it hits, most of the energy goes into thermal energy. It heats up the ball, whereas this one is able to store the energy and then send it back out. So understanding how an asteroid would behave, we have to also understand its composition and its structure to understand how a collision would affect it. Back to Mary.
Okay, so yep, like you said, there's a lot of factors that go into it, and I guess also, as you could probably have guessed, ramming a spacecraft into an asteroid is a little bit more complicated than throwing a medicine ball to a physics teacher or bouncing a ball. So that's where our work comes in. So at Livermore, asteroids are big, complicated structures, as you probably saw in that close-up picture that Megan showed you. There's a lot of things going on there, and you want to know exactly what's going to happen when you ram your spacecraft into that asteroid, because the fate of the Earth is at stake, and NASA might not have another rocket for you. So in order to do that, you want to make sure you know exactly what's going to happen, and the best way to do that is to run lots of simulations on what might possibly happen here on Earth while you still have time. And these are big, complicated simulations because asteroids are big, complicated structures. And so therefore, you need really big computers to run these simulations. So Livermore National Lab has some of the most powerful supercomputers in the world. And occasionally they let us run some of our simulations on these, amongst some other things. And as a result of those simulations, we have some idea of what might happen at the moment if we were to try and throw an asteroid or throw a spacecraft at an asteroid. So right here, this is an example of one simulation that we might do. It's in 3D. And it's a very simplified version. So the gray ellipse that you can see on there is our approximation of an asteroid. Obviously, it's not the best approximation because asteroids are made up of lots of different boulders and things and different materials. But we're going to start with this for now. And really, the only thing that we want to understand about this simulation is what were to happen if we were to, say, impact a spacecraft at an angle. And instead of hitting it directly right on the nose, what would happen if we kind of like glanced at it a little bit, or if it wasn't a direct hit? And so I'm going to play it. And the purple area is where the spacecraft would have hit. And the purple material that's coming off represents the material that has the most momentum moving in the direction from where the spacecraft came from. So it's moving in a direction that's imparting momentum in the opposite direction to the asteroid, so it's helping you. But all of the gray material is stuff that is moving in the same direction as the asteroid, so it's not actually giving the asteroid any boost of momentum. So you want to know how much extra material and extra momentum boost you're going to get, say, if you were to not actually hit it right on the nose like you were originally intending. So that kind of error would be important to take into account. These are some other simulations that we might run on our really big computers. Megan mentioned that Japan has actually sent a mission up to an asteroid to take a good look at it as well, and it's pictured there on the left, and it's called Itokawa. And it's a whole lot different looking than Bennu. Bennu was kind of a little bit uniform, almost spherical, pretty nice. This one looks a little bit more like your thumb. It's got lots of boulders sticking out of everywhere. But it also has like some finer material, and that's covering other larger portions of the asteroid, so it's not evenly distributed. And so if we were to have to, say, deflect this one, we would really want to know, like, what would all of these different boulders, what effect would they have on it? And then the shape, too, even though we don't actually simulate it here. So the simulation on the right is something what we call rubble pile structure. And how we would do it is all of the red roughly represents simulated rocks, all of all different sizes. And so we stick those in, and we say, OK, now fill the rest of the empty space with kind of like matrix material, and just fill in all the gaps. And so great, all right, so we have that simulation set up. And then the blue little thing on the top is roughly what your spacecraft might look like for scale with your asteroid. It's pretty tiny, looks a little sad. But with enough velocity, you would be able to make a difference. So the idea is when you run this simulation, you run it with the highest resolution that you can possibly have, right at where the impact site's going to be, and then maybe a little bit less resolution on the other side of the asteroid where nothing's happening. And then you can roughly get an idea of how much velocity is going to impart and what effect it's going to have on those boulders as well. So we do a lot of simulation support, and one of the things we do simulation support for is something that NASA is coming up with right now. And so they are intending to do a test of this technology within the next couple of years. So there's an asteroid out there that they're going to send a spacecraft to, and they're going to try and nudge it a little bit, not while it's impending to the Earth and like it's an emergency. They're just going to do a test. And it's called DART. So I'm going to run a movie right here for you. So they're going to send up their spacecraft, and it's going to head over to this tiny little asteroid over here, and it's going to bump into it and be crushed. And then, of course, there's going to be a little bit of an ejecta plume, which will give it an extra boost of momentum, and that's going to change its trajectory. And they're going to be able to tell what the change in trajectory is from Earth. And how they're going to do that is this asteroid is actually quite special. It's a double asteroid. It's called Didymos. It's got a big normal asteroid in the middle, and then a little moonlet, which we've nicknamed Diddy Moon, even though it's not actually its name. It doesn't have an official name yet. And so the idea is we're going to hit the little one, Diddy Moon, and because we can actually observe the orbit of these two asteroids from Earth, we would be able to tell once it's hit whether that orbit has changed. And then we can have a rough idea of what has happened. So this is due to launch pretty soon in July of 2021, and then it'll arrive and impact at the asteroid in roughly October of 2022. So we do a lot of simulation support for this mission, and we're going to continue to do it up until and after they impact, so we can tell them roughly what to expect, and then when it happens, what we roughly think has happened. So all of that's great, but what if, say, a kinetic impactor won't work? What if you don't have decades? What if, say, NASA looks into their telescopes and they say, oh no, we see an asteroid, and they go and they do their calculations, and they come back and they tell everyone, we have maybe like 5 years We don't have that long. We don't have, it's too big. You can't send up a kinetic impactor. It won't be enough. What do you do then? So your biggest limiting factor in that case is what can you actually launch from Earth to save you? So we've been talking about energy in terms of tons of TNT, which we would also call high explosive. So if you were to stick a whole bunch of TNT on your spaceship, right here in purple is roughly how much energy efficiency you would have from that. It's about 6 megajoules per kilogram that you can stick on your spaceship. So that's not very much, at least compared to a kinetic impactor. If you put a kinetic impactor on a spaceship and get it going to about 10 kilometers a second by the time it reaches your asteroid, that's maybe about 50 megajoules per kilogram of energy efficiency that you can put on your spaceship. So, but if that's not enough, what do you do? What would be enough? So there's a third option, the nuclear option. You can stick a nuclear device on your rocket, and it will quite literally be the biggest bang for your buck. From there, you would get about 4 million megajoules per kilogram, which is about 100,000 times what a kinetic impactor could give you in terms of energy efficiency for deflection. So, all right, so we've got a nuclear device. We're going to stick it on our spacecraft. So we'll go back over to NASA and say, hey, we need that rocket back. We'll stick our device on there in our spacecraft, give NASA back their rocket, because you never know, you might need it again. And we'll send our spacecraft back on its merry way to the asteroid. And then there's 2 different options of what you can do with your nuclear device. The first is called nuclear deflection. And it's a little bit similar to a kinetic impactor, where the idea is you want to keep the asteroid intact. You don't want lots of fragments flying around everywhere. You want to keep it together. You just want it to be not heading towards the Earth. And so the idea is you'll detonate your nuclear device kind of far away from the asteroid, and it will emit lots of neutrons and X-rays and gamma rays. And all of those things will impact the surface of the asteroid, and they'll heat it up. And some of that material that's on the surface will melt, and it'll vaporize, and it'll do something we call ablate, or just kind of float away. And because momentum works in both equal and opposite directions, that momentum of the material going away will also be imparted in the opposite direction of the asteroid. So you will give it an extra velocity boost. And the idea is, if you'll do that enough, it'll be enough to move it past, increase the velocity, and so it thus does not hit the Earth, and the day is saved. So yes, even though you do have a lot more energy efficiency from a nuclear device, there are still lots of questions to ask. As Dan mentioned, the composition. We have some samples of asteroids that we can collect from ones that have hit, but this is a biased sample of ones that have hit Earth. These are ones that have not burned up in the atmosphere, so they're mostly like metal, for instance. So all of the ones that burned up in the atmosphere, we have to actually go to an asteroid and bring it back on a mission, which is difficult and expensive to do. So we don't always know what asteroids are made up of. And then it's even harder to know if you're running out of time and there's an asteroid heading this way, what it might be made up of, out of. So that's a good question to ask. How will the velocity change that I'm trying to give it be impacted by what it's made out of? And then the structure. So when you take pictures of asteroids, even if you get to get really close to them, you don't actually get to see what's inside them. And there's a lot of theory as to what goes on inside an asteroid, but it's just theory. No one's actually gone and sliced one in half yet. But say, for instance, the whole thing's just kind of like roughly small rocks, pebbles, all things that aren't very dense, and it's just kind of being loosely held together. Or what if, for instance, say, there's like a really dense metal core in the middle? So wouldn't you like to know, say, when you're trying to deflect this asteroid, if it's like you've got a really dense core that you're trying to compete with, or if the whole thing's just kind of stone? So you would want to know. And then shape. So as Ida Kawa kind of showed, asteroids can be all sorts of different shapes. So this one is actually a model of a real one. It looks a bit like a rubber ducky. If you were to try and melt material off of this kind of weird shape, it would matter where you detonated your device, because if you do it, say, for instance, on the head of the rubber ducky, the surrounding area of the bilobe underneath it would be in shadow, and you would not get that extra boost from that surface area. So also important to know. So this is an example, another example of a simulation that we might run. It's a very simple one, and it just explores what the different compositions of asteroids, how that effect might have of the material melting off of it when you apply all the radiation to it. So we've tried on the right is a pure metal asteroid, and then on the left is a stone one. So the way that the particles work is most of what comes out of a nuclear device is X-rays. And so those don't, because they're just light, they don't penetrate very deeply into whatever the asteroid is made out of. But if it's metal, then it's particularly bad at absorbing that energy. And so all of that energy will be deposited on a very, very thin layer on the surface of the asteroid. But it'll be really, really hot, and it'll blow off really quickly, which here in red you can see it's a whole lot hotter. But if you have stone, the light can go in a little bit deeper. And even though it doesn't get as quite hot, you end up having a lot more material, and the deflection is larger. So it depends. This is your other option, and this is probably the option that Hollywood has primed you a bit better for, and this is called nuclear disruption. And this is what you do if your asteroid's a little bit too small. It won't hold together well enough for you to nudge it hard enough to actually get it out of the way of the Earth. So the best thing you can do is just bring your nuclear device up really, really close, and then blow it up. And then all of that, as much of energy as you can get, will be imparted into that asteroid. There'll be kind of a shock wave that'll go through it, and a lot of material will melt and vaporize, and it'll literally be blown to bits. And that's the general objective. So, and even though this might seem like this will work, like there's no questions here, everything will be fine, it is still worth doing the simulation first to make sure that you understand what's happening. Because again, we don't know very much about these asteroids, and the way it fragments would be important to know. But provided you've done it correctly, all of the little fragments that are left over from the asteroid will miss the Earth entirely, and the day will be saved. So this is what a simulation of a nuclear disruption might look like. So on the right here, you can see shortly after the detonation, the pink material is moving at about 10 kilometers a second. So that's going really, really fast, and the asteroid's breaking up quite quickly. And then eventually it's going to fast forward, and then you can see the shockwave penetrating deep into the asteroid, and it's starting to fragment. So on the left here is a close-up of what that might look like. So in this simulation, from this snapshot, what they've done is they've color-coded and found all of the different fragments that are left after the shockwave, or as the shockwave is going through the asteroid. So all of those fragments you want to keep track of, because those are all the little pieces that are going to be left that may eventually hit Earth. And you want to know how big are they, where are they going, things like that. So those are also the types of questions that we try to answer. So, which brings us to our last question. Which option of these is best? So we've given you three, and each of these are better in different scenarios. The first one, the kinetic impactor, that will only really work for you if your asteroid is about less than 300 meters in diameter, and if you have decades of time for the small difference in velocity to make a big enough difference. So the one after that, nuclear deflection, that'll work for bigger asteroids, and if you still have enough time. So there you'll just melt the material away, you'll give it enough velocity, it'll be a big enough push, but the asteroid will still stay together and it'll still miss the Earth. The other one, nuclear disruption, those will work really well for like smaller asteroids, for instance. That they're so small, their gravity isn't strong enough for them to hold together, and you don't have time to give them a tiny nudge. You need to give them a big nudge, so you're inevitably going to break them apart. So if you're going to break them apart, you might as well do it with feeling and with purpose. And of course, all of you have probably read the last option, which we've missed out on all of these other options. So our best course of action then is to brace for impact, which is the last and kind of not the best option. But Livermore actually also does simulations that would help with responding from an asteroid that's still coming, but we want to do something if we can't actually get it out of the way. So then we have another demo for you. We hope you've been paying attention.
So we thought we'd give you a chance to observe, and some of you try and intercept an asteroid and deflect it. So it would be your chance to be a planetary defender. This is the Kinetic Impactor. And so this is what we're going to use to try and deflect an asteroid. And we'll bring the asteroid out here in a little bit. And so this is Earth. And so you're going to be trying to intercept it. We're going to do this a few times, and then once we're done, we'll want all the kinetic impactors to make their way back up on stage, as well as the asteroid. So I'll just distribute a few of these here. If you don't want one, just hand it to your neighbor. If you want one, raise your hand. I'm sort of can't get it back that far, you guys, so sorry. I think we're going to need a lot here because I just heard from NASA it's a pretty big asteroid heading our way. And there we go. Oh, here it comes. I was right. It is a large asteroid. So now we're going to have a little fun with this, but we can also sort of learn about the challenges of intercepting and deflecting an asteroid. The best place to try and intercept an asteroid is its highest part, also it'd be called its aphelion or apogee, depending on what it's orbiting. And so you'd try and hit this when it's at its highest over you. However, that's the hardest place to get to, right? And if you throw your kinetic impactor, it's going to have less energy when it hits. So you could wait for it to get closer. You're more likely to hit it then, but it's harder to deflect. So I'll leave that up to you. And if you don't have a kinetic impactor, well, hopefully your neighbor will protect you here. We'll see. Oh, very good. Hey, it worked. It came back. Although I saw another technology there, the hand. Unfortunately, Earth doesn't have a giant hand to come out, but oh well. So here we go again. Get ready? It worked. One more time. I'm going to try and throw it really high here. Maybe. They're out of luck then. Okay, good job. Any others out there? See the last chance to hit it. I'll just hold it. There you go. Oh
no.
Okay, good job.
All right. That was awesome. So brace for impact, that sounds a little scary, but a big part of being better prepared is being able to model the consequences from something if we can't prevent it from impacting the Earth. We talked earlier about Chelyabinsk and Tunguska as two examples where a lot of the energy was deposited in the atmosphere, and that's true especially for things that are 100 meters or smaller. And we're going to show you a video here of some of the recent simulations been done within our group, looking at how things break apart in the atmosphere and how they explode. And this is important to know what kind of effects are going to be found on the ground. So you can see the bow shock forming. This is an asteroid coming in at something like 20 kilometers per second. And the details of how it breaks apart and fragments into many pieces are really driven a lot, actually surprisingly so driven by the details of its shape, its characteristics like its porosity, about how fluffy it is. And so this is a 2D simulation as an example, but it is definitely a 3D problem because asteroids come in at very oblique impact angles, and we're scaling up to be able to do 3D simulations like this in the future. If something's going to impact the Earth, a lot of Earth is covered with water, so there's a good chance it'll impact in the ocean. We want to know what kind of waves are going to be generated in that scenario. And it can generate things that are like a tsunami. It's not technically a tsunami because the cause is not tectonic plates, but the after effects can feel like a tsunami. So here's a simulation starting off in the lower left, an asteroid impacting the water. You can see the water shown as red and the atmosphere as blue. We have to do that in a shock physics code. And from that code, it creates a source that's then handed off to another code that specializes in tracking wave propagation over very long distances. So in this case, this is from a Planetary Defense Conference scenario, an exercise that we do at all of our planetary defense conferences, where we were in Tokyo that time, and the target was Tokyo, because it helps create a sense of urgency, I think. And it was coming. This particular one didn't impact Tokyo, but it impacted in the Sea of Japan, which you can see in the upper right there. That red dot is right where it impacted at 0 hours. And then stepping forward in the next few hours, you can see the blue and the red are showing where waves are propagating through the Sea of Japan and then inundating parts of the coast. And our group can actually make very detailed models from Google Maps looking at what areas are inundated in these scenarios. So that's really important to have an evacuation plan in place, be able to secure infrastructure like nuclear power plants, so we're prepared. Another aspect of consequence assessment is perturbations to the global atmosphere. So an impact in the ocean will vaporize a lot of water and inject it into the atmosphere, and certain things can cause problems down the road. So in this example, it's an impact into the Gulf of Mexico, and we're injecting a whole bunch of chlorine into the atmosphere. We're tracking chlorine abundances. Chlorine is really unfortunate because it eats up the ozone very efficiently, which is not good. And it also can create long-term changes in the temperature of the atmosphere. So again, this is a handoff between two codes, a shock physics code to model the initial impact, and then another code that looks at the global circulation models that we use at the lab to see what the long-term evolution will be for the material in the atmosphere. And for consequence assessment, FEMA, the Federal Emergency Management Agency, is very interested in that aspect of planetary defense. They want to be prepared. And FEMA sits within the Department of Homeland Security, which is on the left here. Where we sit at Livermore is within the Department of Energy, which is shown on the right hand, and more specifically in the NNSA, the National Nuclear Security Administration. And kind of coordinating all of these interagency activities on planetary defense is NASA, more specifically the Planetary Defense Coordination Office, which their logo is in the middle on the bottom there. They were stood up pretty recently, and so it's recognized there's a lot of important interagency work being done between all over these different parts of the US government, so they help coordinate that. Planetary defense is a very global problem, so we have these defense conferences every 2 years. They're typically in international locations. The last one was in Washington, D.C. The next one will be in Vienna. I mentioned Japan. This one was in Italy. And these are all the flags from the different countries that participate in these, because everyone has a stake potentially if there's going to be an asteroid impact somewhere on the Earth. So just to revisit this action plan slide, the US government takes this very seriously, and we kind of talked through a lot of these components of planetary defense where we are contributing to at the lab, and our interagency partners and partners across the globe really are contributing to different pieces of the problem. Finding the asteroids with telescopes, having better computer simulations, better mission technology to go out and test some of our deflection methods and know more about asteroids ahead of time, cooperating internationally, and having emergency procedures in place. And I wanted to briefly talk about how Mary and I are just a few of a much larger team at Livermore, and I have a few of the other folks that work with us on this slide, but the intent here is to show the diversity of academic backgrounds that folks come from physics, astrophysics, engineering, materials science, geoscience, or planetary science. No matter what your interest is, there's a chance that your field of study, your expertise, can lend some important insights into this problem. It's a very interdisciplinary problem. And this is just kind of silly. We get this a lot from the media. It's such an exciting issue, planetary defense, and they'll call us the planetary defenders and make a comparison to superheroes, which is, Mary and I definitely don't think of ourselves as superheroes, but I did want to try to inspire a lot of the young people here today that you might be the superheroes of the future, because we don't know when we're going to need planetary defense. It might be 25 years from now, 50 years from now, 100 years from now. And just to inspire you to really enjoy your math and science classes, because those skills that you learn could be used for some of these really interesting problems. Thank you so much for your attention, and we're really happy to take your questions.